Okay, so welcome everybody to today's seminar. I have the pleasure to introduce you to Valerio Marra, who is a professor at UFES, and today the title of his talk is Cosmological Tensions and Inhomogeneous Cosmology. So thank you, Valerio. Please take it away.
Thank you, Vicente. Thank you for the invitation. It's a pleasure to be virtually there. Santiago is a really nice city. And okay, so we'll be talking about a little bit cosmological tensions and then inhomogeneous cosmology. That will be a broad overview. So an outline of the talk will be, I'll start with inhomogeneous cosmology. I'll introduce the simplest approximation, the LTV model. Then I'll go through standard model tensions anomalies, and then we'll focus on the large-scale structure in inhomogeneous backgrounds. So inhomogeneous cosmology is not a mainstream cosmological field. It's a little erratic, right? You risk ending up like this guy if you're not careful. So what is it? It is the study of the universe without assuming a priori the standard homogeneous azeotropic metric that is FRW. Usually you just assume it and you work within this background. So this is the main difference. I still believe in the Copernican principle, which of course would imply FRW at some scale. The difference is that the view here is that the Copernican principle may be valid at much larger scales. You may have these inhomogeneities on larger than expected scales. So what are these inhomogeneities? These inhomogeneities, in my view, so this is very my personal view. If you talk with other people working on homogeneous cosmologies, they will have a different view. So my view is that these homogeneities you can imagine them as some weird stuff with no standard amplitudes and phases, right? So this don't need to be very high amplitude, just to be beyond what is expected by standard inflationary paradigm. So you're gonna, what characterizes this inhomogeneous cosmology is some coherent bulk flow and also bulk flow for coherent and very coherent perturbations on some very large scales. Of course, once you drop the FRW assumption, everything becomes extremely difficult. So a simplifying assumption is that you have near FRW at early times. Okay, so when you go back at the CMB time, everything is still fine, linearly homogeneous and isotropic, even though with different spectra. And it is not the Beck reaction proposal, that's completely something different. So why should one care about inhomogeneous cosmology? Well, because deviation from FRW, even small ones, would impact understanding of primordial physics, for example, inflation, and also the reconstruction of the dark matter and dark energy, which are really unknown. Moreover, there have been some hints of dark-scale homogeneities in anisotropies, and this comes from the standard model tensions. So what is the lambda LTB model? So it's a spherical cow of the inhomogeneous cosmology. But I will argue along during this talk that it is a spherical cow, but it is a useful spherical cow. So it is just the lambda CDM model plus a spherical perturbation. It can be over density or under density. So here I'm showing some simulations. You see that the contrast, the central contrast, goes from positive to negative, from left to right. So you got a big cluster, big over density, super mega cluster. And on the right, you have this huge under density. It's a hole in the universe. Of course, these extreme cases are completely ruled out by observations, but I will argue that a small contrast, say a few percent of contrast, are not. So so LTB is a general relativistic solution of Einstein's equation, so you know everything exactly. And the modeling that I will adopt is the one of a compensated profile. Compensated profile, so you got the local contrast in blue here, You see, this is the radius. This is a 2 gigaparsec structure. And then locally, there's another density here, and then there is a compensating overdensity such that you match the metric at a finite radius. So when you pass this point, this is just FRW locally. It's possible to distinguish it locally, of course, not globally. And on the right is the opposite for an overdensity. You see, it's an overdensity that is compensated by an underdensity, and then matches the background. And this compensation, it's a trick mathematical to ensure stability, because you match at a finite radius, so you really know how is the background at this point. It's also realistic because you do see a void surrounded by filaments and denser structure that try to compensate for this underdensity. So it's not a too bad picture. Then you see the omega, density parameters, how they behave. Of course, you got a lot of curvature at the center in both cases, positive and negative. And then here, just to show the Hubble rates. So features of any inhomogeneous model is to have different Hubble rates, right? This is local anisotropy. And in particular, you see that this is the perpendicular to the line of sight, and this is the parallel to the line of sight. They're quite different. Of course, this is an extreme case. And in this, for example, in case of this huge void, you see that locally you have a higher than outside expansion rate, which we can connect later to the Hubble tension. Of course, the opposite is for the local overdensity. The equations here are simple, so just one of the simplest solution of general relativity. And here are written in order to trick the reader to think that they are almost identical to FRW, because it's written in this way, so that it really looks like. The difference that you have two scale factors, parallel and perpendicular, which give rise to two Hubble rates. And you have R dependence everywhere, in the curvature, in the scale factor, in the Hubble rates, in the density parameters, and so on. What defines a NFTB solutions, removing apart from gauge freedom, are two functions. The curvature function, which really is generalized the fixed curvature of FRW, which by giving a non-trivial curvature function, you excite a growing mode in the solution. This is just a purely growing mode. On the other hand, you can also mess up with the Big Bang time, the time of the local singularity, and this will source a decay mode. As I want to have early FRW cosmologies, I don't want to have any decay mode, otherwise I'm gonna have monsters in the past. So I'll kill this degree of freedom. And then my only freedom is to choose a suitable curvature function. And here I use this this functional form that guarantees that at the given finite radius, I match the background curvature, which in the case that I'm gonna show is always flat, just flat on the CDM. Okay, now let's go back to, let's talk about a little bit about the tensions. So there are the very old and very famous and very studied CMB anomalies, and it's really interesting. And there is the cold spot, there is the lensing amplitude, the hemispherical anisotropy, and it's a very involved, interesting subject. If you're curious, there is nowadays a relatively recent review by Leandros and collaborator. I really here there is a lot about anomalies, also curiosities. It's a nice reading. Then there are the large-scale dipole anisotropies, which I will focus on. And then using as tracers, radio galaxies, and quasars. Then there is the bulk flow, which I also will mention. Then there are the small-scale CDM problem, like the too big to fail, the cusp, core, and this is mostly related to our understanding of dark matter and hydrodynamical, and the feedback mechanisms given by baryons at small scales. Then there is the famous sigma 8 omega matter tension, or SA tension, and this This is not a very strong anomaly, but it's basically that the CMB predicts a stronger clustering with respect to weak lensing, for example, from the Carnegie survey. Then there is the super famous H-naught tension, which I'll mention later. Then there is the integrated structural effect anomaly, which is also very interesting. And there are many, many more. And I think the anomalies are really we should really push our understanding. However, bear in mind that these tensions that come not from a statistical robust study, but they are just serendipitous. I mean, people just found these things and look at those. So this tension may suffer from what is called the significance inflation, also known in particle physics as look elsewhere effect. Meaning that it's you never publish results of a tension that you didn't find, right? There is not such a journal. So this inflates the perceived significance of these things. And so bear this in mind. If you like XKCD, 882 is a nice example of what is significance inflation. I encourage you to check it out. Okay, so dipole anisotropies. So here the name of the game is the Ellis-Baldwin test, back from the early 90s, I think. So the idea is very simple. The velocity estimates, now you can measure the dipole due to a velocity, right, on stuff in the universe. So velocity estimates from these tracers should all agree, right? If the FRW is correct, is the correct description of our universe. In particular, they should well agree with the CMB dipole, which is one of the best measured quantities in cosmology. Okay, so this is our Earth. Here we got, say, the LRG, the luminous red galaxy beam. Here the quasars beam. Here there is a CMB. And we observe, due to our own velocity, distortion in these distributions. And you very well know the dipole one from the CMB. And what you should infer is that the velocity given by green, red, and yellow are the same. Okay, so this is very simple. So regarding number counts above some flux threshold, that is what traditionally has been done. So you assume some spectrum with some spectral energy distribution with a given power law. You assume that the number counts go according to a different power law. And then you can connect the observed number counts to the rest frame ones, given via these power law indices. And you do the math, and what you find out is that the dipole anisotropy that you should see is given by the simple formula. It's basically a constant given by some astrophysical stuff multiplied by the velocity of the observer. And this velocity is what should agree with the one that we measure from the CMB, very, very high accuracy. Now, the issue is that during the past many years, 20 or so years, there have been consistent hints that from number counts, you get a larger velocity than predicted, than expected from CMB. You get basically the same direction, but with a higher amplitude. And a key paper was the one by Sekres and collaborator that made the news in 2021, because they, using the catwise quasar sample, they found a measurement of the dipole, which was 5 sigma of the CMB expectation. Okay. Then there was another paper by the group of Dominique Schwartz and collaborators using radio galaxies, and they found also 5 sigma. So people, during those months, I remember that people were really talking about they really this made the news. And the error bars are large, and even though the effect was consistently larger with larger error bar, was also small significance. So as always in astronomy, everything is about systematics and error bars, right? So are these error bars trustworthy? Is this really 5 sigma? Are they systematic? So there's been a lot of discussion on this with for the literature. This is what the 5 sigma measurement by Domin Schwartz, but this was stolen from a poster during a seminar by Pedro Ferreira, but I don't think this has been published yet. All right, so why this is interesting for inhomogeneous cosmology? So think about that. Imagine that there is a spherical cow structure in the universe, and this will be given by this black circle, just to give an idea, right? This one will be the center. Now, we may live out of center from the structure. And if that's the case, it is possible that the velocity that you infer from the dipole in the CMB is different from the one of the equators. Just a matter of choosing the profile, the size, the position with respect to the center. So it's a simple model for this anisotropy, and there is even a paper that they try to look at this. Okay, so with Pedro Ferreira, we tackle this problem from a different point of view. Instead of looking at number counts, we look at.
Excuse me.
Sorry. Okay, we looked at the redshift, the number counts. You know, the problem number counts is that you really don't know. There are some systematics that can be problematic.
Ask you a question, Valerio?
Oh yes, please.
Oh, hi. Do you hear me, Valerio?
Yeah.
I think okay, thanks. No, I wanted to ask you if there is an assumption about the direction there, because you're comparing the velocity, but do you need to assume something about the location of the where you're moving in this model that you're presenting in the next slide?
This one. So no,
Yeah.
here this is just a cartoon to give to give an idea that you could model such an effect with LTB. But of course, if you we didn't carry out this analysis yet. But what would you do? You would put all your data on the sky, right, with your angular coordinates, right, a sanction declination, and then you would see that there are dipoles from various traces. You got quasars, radiodipoles, you got supernovae, you've got the CMB, of course, X-ray. There are dipoles on the cluster scaling relation. This is was a recent interesting work, for example. So I would put all this data on the sky, right? Then you got your lambda LTB model with basically 3 extra parameters, which would be the size, the depth, your position with respect to your distance from the center. Of course, also the position with respect to the sky. And then you would run an MCMC and look for the best model that would fit your data. So
Okay.
that's something that I will do. But as I'll show you later, once you drop FRW, everything becomes so complicated and takes so much time, so much coding for everything that we didn't do this yet.
I see. Thank you.
Okay. So here, instead of looking at number count, we did something simpler that look at the distortion on the redshift because of the peculiar velocity. So you can look at the dipole on the Doppler modulation of redshift. As simple as that. And here we looked at the BOS and eBOS data. So these are the tracers shown here and the redshift range. This is the footprint, which is large but far from being isotropic, and this introduces several difficulties. So we introduced a new estimator because of this, especially because of this anisotropy. So this chi-square compares a given dipole, this delta one is your dipole velocity, for example. It compares a given trial vector with the measured redshift. So you compare this measured redshift with the model for this dipole modulation. But how do we do that? We need to do this. There are a few tricks that are important. One is to use the undoppler monopole in order to compute the dipole on top of it. This is necessary because of the limited footprint. You cannot compute the monopole on a given slice because you are missing pieces of the sky. So you need to unboost your redshift, compute the monopole, then boost it again and compare with the data. So we test this. This is a data intensive analysis, and Pedro did a wonderful job. And also you need to split to analyze separately the north and the southern hemisphere, as they're not perfectly matched in normalization. And it's a huge pipeline. We work till the very end only with mocks, using the 1,000 mock data mock catalog from eBOS and BOS. And to create we also created maps that would unbias the analysis, given the biases that may be introduced by systematics, especially anisotropies in the tracers distributions. So all this was done on mocks to correct and calibrate the measurements. And then at the end, we saw like a quarter of a million CPU hours in that analysis. And then in the end, we applied this to real data. And the result was that we found from eBOS a good agreement with the CMB. Of course, agreement mostly because the error bars are large also. But anyway, we didn't find that very high values that number counts analysis found. And with BOS, we found a deviation, especially in the direction of the dipole, and we suspect that there are systematics in the BOS set, and not to enter in details now. But putting these results together with the early ones, a result to find that a very dipole value that is very compatible with the CMB. And even more important, that is quite incompatible with the quasar measurement and the radio galaxies measurement from Sekrest and Wagenveld. And so our result, again, was a blind analysis, are in favor of large-scale homogeneity and isotropy. But of course, one really has to repeat this with the higher density of redshifts, and I'm sure that DESI people will look at this and improve much on this result. Okay, next, the Hubble tension, super well known. This is a famous plot, I think, from Wendy Friedman. And well, back in the days, everybody was happy with the same H0. Then after Planck, in 2013, we started seeing discrepancy, which now reached 5 sigma, or better, 6 kilometers per second per megaparsec. So a simple solution, as I already mentioned earlier, is a huge underdensity, and we live at the center, close to the center. Now, in this case, if you have such a huge underdensity, and deep especially, you cannot really go very far from the center, because otherwise you're going to see a very strong dipoles in everything, especially CMB, and you're going to need an incredible fine-tuning to fix that. So it's a very contrived model. It's a bad, from the theoretical point of view, it's a bad model. But nevertheless, it's would be phenomenologically interesting to look at this. So you see that if all your local tracers, say the supernovas that the SHOES project uses, the Cepheids, everything is within this red range, they would measure 73, but then the CMB would measure 68 because it's outside, right? So that's a very simple explanation for double tension. Of course, your normal structure to give you these effects. It's called cosmic variance on H0. It's been studied since forever. And some years ago, we updated those analyses, and there was also a lot of work in the literature. And we found that at most you get 1 kilometer per second per megaparsec of this cosmic variance, this systematic effect on H0 given by the standard structure in the universe. And this is not enough to explain 6 kilometers per second per megaparsec, because this is really a maximum one. You expect 0.5. So this is really, it's working. But what about, okay, let's drop standard cosmology, standard perturbation, standard inflation. Okay, let's see, what about an arbitrary inhomogeneity? Well, if you then just put anything, and you only include low-ratio supernovae and the calibration from the Cepheid, what you get, and the CMB, you can just get the CMB to have some basic constraints on the other parameters. What you get is that your MCMC tells you that you live in an underdensity, very large one, and with a depth of, say, minus 0.15, 2 in this case, which is very at odds with what you expect from homogeneity, which is the blue contours. So this blue contour would be the CMB plus the Copernican prior. Copernican prior is simply the CMB spectrum of perturbations applied to our local neighborhood. Because if it is homogeneous and entropic everywhere, what you say as CMB should also be valid at your own position. So this is the standard stuff, the green one. You see there is quite a disagreement. Okay, so if you have a beyond lambda CDM under density, you can explain the Hubble tension. But this is true only if you consider this limited range of supernovae. As soon as you add all supernovae, you go from red to black. You say goodbye to this model. I mean, you go back to the standard picture. The black contours very, very well agree with the green ones. Basically, what is the message here is that nowadays, with the Pantheon dataset, you map the luminosity distance so well, along all redshift, and the standard candles are so well standardized, and you believe them because they pass many tests, that you cannot see, you don't see a jump in the luminosity distance at any redshift, so you cannot really accommodate. If you restrict only between 0.023 and 0.15, you can do here. You put a void, and that's it. Once you put the other supernovae, as these supernovae, they share the same absolute brightness, you cannot do that anymore. So this is not really a solution to the Hubble tension. Side product of this project was to map the local environment, our local space-time, and we found that yes, we do live in a point which is stars, which are in agreement, with the standard stuff. But yes, we do live in local underdensity, but it's much shallower than what is needed for double tension. It's a 5% shallow underdensity. And this is interesting because this is in agreement with the work by McAlpine. So they do constrained simulations. They do method simulation and they constrain initial conditions so as to agree with what we see in the universe. And they also find a 5% underdensity. If you want to do a better modeling, you want to stretch the cow, the spherical cow, have an ellipsoidal cow. If you're interested, you can have a look at the work by Leonardo Gianni in this paper, which is quite interesting. Next, there is the large-scale bulk flow. Again, this is a working project. I don't really have results. I'm just flashing some stuff. So what is the bulk flow? You average the velocity flow on a given volume. And then you compare it with predictions from lambda CDM, expectations. And you see here that expectations are in these lines, they're red, blue, and they're quite far from the measurements. You can see also here. So this was this work was then repeated with the galaxy MOX for more robust analysis, and they found lower significance, but still some effect. So there is some bulk flow, which is at odds with what we expect from lambda CDM. And again, the spherical cow can help you with that. Why is that? Because you can imagine to have this huge structure, and then you live in your neighborhood. It therefore is moving, with respect to the CMB background and some other matter frame. And again, this is a very simple modeling that could give you some insight. We start having the dipole anisotropy, the bulk flow, and it's not obvious that a single inhomogeneous model can explain both. So it would be also a good way to exclude these kind of models, because once you can be competing trends in your multidimensional space when you try to fit for the data. All right, let's go now to the part of the large-scale structure on inhomogeneous background. So far, all the results were obtained using background observables. But the future is given by, the Canny survey, DESI, LSST, Euclid, given by perturbations. And we do not know how perturbation grow on a inhomogeneous background, because even at the linear level, you have mode coupling between different wave numbers, in particular between scalar and tensor perturbations. So the idea here was to study perturbation via numerical cosmology. So in collaboration with the people from Trieste, I ran a suite of 68 simulations. It's a Pathfinder suite of simulation because they're quite boring. It's the same profile and the same initial conditions, just changing the size and the depth of the structure, but keeping cosmology initial condition and standard initial condition fixed. So this is a Pathfinder approach, and nevertheless, there are lots of data products that, if you're interested, you're welcome to join the project. So we got full snapshots, Halo Finder with lots of properties, and lens planes that can be combined in any way you want, because these are all periodic boundaries conditions. So you can mix lambda CDM and lambda LTB lens planes on the light cone in the way you want. So how were these simulations made? So it's a neat trick that was pioneered by Alonso and collaborator many years ago. And it's thanks to the spherical symmetry of LTB. So the spherical symmetry in this exact GR solution actually eliminates most of GR degrees of freedom. So it's almost a Newtonian structure, even though it's a full GR solution. And this means that you can actually simulate the evolution of the LTB background using a Newtonian n-body simulation, which is something non-trivial, but this is basically due to the spherical symmetry and the fact that the matter content is just dust and the cosmological constant. So how do you do that? Then you just feed a standard n-body code like Gadget. We use in particular Open Gadget 3 with special initial conditions for which you use the code Falcon IC, which are basically just the standard one, your Gaussian initial condition for inflation, plus a lambda LTB deformation, which push around matter particles and also changes the velocity. Okay, you can see that here there is a deformation at the center, but the arrows outside the inhomogeneities are the same as in other CDM. Okay, so they all share the same seed. So this is a simulation from box 1. So what do you see? So my main message here regarding growth of structure in LTB is that there are two main effects, right? You got different growth. You see that there is less contrast here which is an underdensity, then here, which is an overdensity with respect to lambda CDM. See, here there is more structure, here less structure, and bulk flow. So different from alternative models like modified gravity or interactive dark energy, which they do change growth, they do change many things, but they do not have bulk flow. Bulk flow is something that is characteristic of inhomogeneous cosmology. So bulk flow, it pushes layers of shells of matter around and displaces them with respect to the standard cosmology. So you see that this structure here, see, this has been pushed with respect to the analogous ones in the other simulation. Okay, we see formulas about this in a few slides. So how to model the growth of perturbation? You can work on the full set of coupled equations. It's a nightmare that people have tried. A group of Chris Clarkson, Barterman, they try to tackle this. It's really difficult to have a predicting useful model that can usefully use in data analysis. There is the silent approximation, so which was proposed by James G. Bean, and basically you neglect coupling between scalar and tensor modes. There's the zero shear approximation, and then you can also treat this problem as a second order perturbation theory. First order LTB, second order would be the standard stuff on top of LTB. I focus on number 2, number 3. So this is all based on the pioneering work by James E. Bean. So you do a 1 + 1 + 2 decomposition, you end up with 4 scalars: density, expansion, shear, this electric well scalar. And then you can study the linear evolution. And here the trick is that if you neglect the coupling with the scalar stuff, no, then you end up with this a simple set of ordinary differential equations. And then you can really just solve the evolution shell of matter by shell of matter. Okay, is this justified? Well, is this, there are tests that you can do to see if this is self-consistent. But you can imagine that you start from a background, which is a nonlinear background, which cannot produce tensor because the LTB alone is silent. Silent because it's being spherical symmetric, it does not produce gravitational waves, and as the matter content is dust, does not produce sound waves. So there really no communication between neighboring matter shells. So you got a background that cannot produce tensor, and then the tensor that are produced at first order, you can hope that they won't have a very strong coupling with scalars. And so this should be a good approximation. But again, there are ways to study its self-consistency. And of course, you can compare these results also with the simulation that includes also the GR effects. All right, then you give your initial conditions, and you can solve the evolution of these equations. The way it's been formalized this was via a series of transfer function, LTB transfer function, that will transform, the initial values of the scalars to their values at given time t. Now, if you further assume that shear is low, is negligible, right? Such that this term doesn't impact very much the growth of rho, or the matter contrast, then you can decouple this, and you end up with the equation that is formally identical to the one in lambda CDM. The only difference is that these local quantities are some effective quantities that have nothing to do with the background or values of h and omega. And moreover, they do depend on R. No? But this R, again, is not a position on the universe, right? It's the internal label for a given shell of matter in this inhomogeneous universe, which undergoes bulk flow. Now, to see if this shear is negligible, this shear, it's the difference between the two expansion rates. You can compare it with the expansion, then you can build this gamma quantity to see if it is small or large, right? Now, how do we compare with simulations? Given the symmetry, it's natural to look at the angular clustering by dividing beams, and then you just use heel peaks to compute to your CLs. What is the prediction? For FRW, is well known. Here, using just a window function, which is a top hat, no, a top hat, a constant uniform within a bin. And this is the matter power spectrum. These are your, to do these integrals you do with the FFT log. There are some smart tricks to create these integrals. So how it is in lambda CDM, in lambda TB? Now, in the zero shear approximation, the spectrum is pretty similar. It's pretty easy. It is this one. Now, it's easier to understand it if I rewrite it, if I open it up and I write it with the individual pieces. So what is it? It is the early time FRW power spectrum given by your primordial transfer function, your primordial power spectrum, the standard stuff, which is now the integral goes over this window function, which is shifted by the bulk law. No? Here it is in R. Here it was in chi. Chi is your moving coordinate, say in the simulation. R is the internal coordinate in the lambda LTV evolution that undergoes bulk flow. So it's shifted by the bulk flow. And it is boosted by different growth because the growth depends on R. Okay, so basically, this is the prediction. It's the standard stuff shifted by the bulk flow, boosted by different growth, which is what we also intuitively saw in the simulation here. Okay, so this formalizes that intuition. So here, these are the CLs. You can model them and match them, but here you cannot really see very well, right? But the trick here was that we ran everything with the same seed. So you can factor out cosmic variance and increase enormously the signal to noise. So let's look at the ratio of the two CLs. But now the ratio is something that is not, it's tricky. It's not like you modify gravity or dark energy models. Why? Because you have bulk flow. So here it's a simple diagram that shows the relation between how much of flow that you had for a given distance. Here tells that the shell initially located at 400 megaparsec is displaced by 100 megaparsec at redshift 0, right? Because you have this, if you have an under density and the expansion inside is faster, everybody is flowing faster outside. So you have this displacement with respect to an analogous model in lambda CDM. Okay, so so you have this deformation. So you need to. So eventually, of course, everything must be compared to in redshift space. Now, observation in redshift and angles. So that's only what matters. Now there you mix many effects, so it's difficult to understand, more difficult to understand exactly what's happening at this stage that we're understanding the growth of structure. Because you on the redshift, you have changes in redshift just because of the large-scale homogeneity. Give you just changes the redshift, and so it becomes difficult to understand which part of the effect comes from which mechanism. So at this stage, we prefer to look at compare according to two approaches. So you can do the easy one, the simpler one that you would do normally in simulation, which is just comparing angular power spectra at fixed distance. No, that's good. chi is your co-moving distance. Let's look at first the CLs at 400 megaparsec and compare them. Okay. The other approach, which I'll argue that is much better, is to compare the same for spectrum relative to the same shells. Now, a lambda CDM simulation, these matter shells are here. If you had a lambda LTB instead, this much of matter, you would find it here at a different chi position. But here they share the same R position, which is this label for the matter shells. Okay, so with the fixed shell approach, I will compare the CLs of this beam with this beam instead of this beam with this beam. And as you will see, the comparison is much more meaningful. Well, as I say, it is best to write the matter wave. So here it is. So on the left is the fixed distance. Of course, you have your model, and no, the dashed is the model for the lambda TB structures. But the noise is so much that you cannot see anything. Basically, because you're not comparing, you're not subtracting the cosmic variance at all, because you are comparing two different shells. You see, if I compare here with this one, these are two different shells. So the small scale phases that are here are not the ones that are here. These are the ones that are here. So you're factorizing only a small part of the same primordial phases that you have in your simulation. On the other hand, if you do this in the fixed shell approach, you almost magically remove everything. You still have some waves because there is no linear coupling, so you cannot do this. No, this won't work perfectly, but too much better agreement. And here is the comparison with many cases. You have here your L range and then various shells, one that is at half the way, one is third the way. And then you have different redshifts on the different columns and different contrast on different lines. So this is the zero share approximation works very well for many cases. Of course, there are cases for which it doesn't work because you need the silent approximation, but this is still, we are finalizing these days. This work is not ready yet, but what I believe anyway is that for most applications for comparing with data, you will just need the zero share approximation because the viable ranges of contrast are at most 5–10%. So in that range, the zero share approximation, we're seeing that is a very good approximation. So that will simplify a lot the coding. Okay, thank you.
Thank you very much, Valerio. I don't know if we have questions. Or maybe someone from the Zoom. Okay, if not, I have a question. I wanted to ask you, like, I mean, I can imagine that one of the big parameters of the model is how large your void is. Is that the most impactful one?
Yeah, so this slide I think may be useful for that. So the simplest possible simplest approximation is that just the size and the depth matter, right? You model a spherical structure over dense or under dense just by its depth, some measure of the depth. We use the central depth or contrast and the size. No, just that. But of course, this is and these are the main, for sure, for any order of magnitude analysis, for any, if a model can do that or that, these of course are the main parameters and are enough. But then if you want to be more precise, and you want to be more precise if you model the local space-time, Then it also matters how the for example, the curvature function in our case is modeled, is parameterized. So the exact functional form. So here we showed two examples. So this, I've shown the equation somewhere. Here, you see? Well, my papers that work use a slightly different equation. But anyway, you got here parameter n. Okay. So there is another function, I believe it's alpha. But anyway, so if you change the exact modeling or the functional form of your cursor function, then you find different results. And you see that here by fixing alpha equal to 0, we find this point. By relaxing alpha to any value between 0 and 1, we find a different point. So when eventually, when you want to do, say that you want to do a better job at describing the local space-time. So what you should do, is to have a bunch of parameters, which is the size, the depth, the distance from the center, the angular coordinates, of your distance from the observer, and also got these 3 degrees. So got 2 plus 3, then 5, and then also at least some other 2 parameters for the curvature function, and then you can fit these to your local observations, and you can do a mapping of your local spacetime. Of course, to do this with the LTB, I think it's like shooting your foot, because why would you need an exact solution with all its complications for a 5% inhomogeneity? You can use perturbation theory, perturbative approach, which is much more flexible. So I really believe that because LTB it was useful for many things, because you can study for example, I'm showing a lot of results for contrast plus minus 0.6, which are nonlinear. But this is interesting to study the validity of the approximations, to explore dynamical ranges and all that. So for investigating stuff, surely it is useful to have that solution, because you have one less unknown, you have more freedom. But if you want to do then some more precise modeling of observations, I think using perturbative approaches is much more suitable. And yes, all this prediction will surely depend from the way, for how you model the contrast, the curvature. You could use a spline method to model that with a few nodes and parameterize with those. And I think that will be much more interesting. Yeah, but so far I haven't seen anybody doing that, because again, it's a lot of work. Every time you drop FRW, you need to write whole new code for everything.
Easy. Thank you very much. Are there no further questions? Okay, if not, thank you, Valerio, again, and for the very nice talk. Thank you.
Thank you, Vicente. Thank you. Hope to see you guys next time in person.